Okay, let's begin. So as I mentioned on Wednesday, the homework assignment number 2 is due tonight before midnight. So the submission deadline is set to 11:59 p.m. And then on Monday, we're going to have a brief quiz just to assess some of the concepts that are included in homework number 2. Homework number 3 is available now, and we're going to talk all about reactors in today's class. That assignment will be back to the standard submission deadline of before our class lecture, so that's going to be due at 1 p.m. And then class next Friday is due, class next Friday is going to be posted on YouTube. I'll be down in Greenville, South Carolina, working on questions for the FE exam at NCES, so I won't be here next Friday. One other announcement that's not listed here is that we're going to have another faculty candidate visiting on Monday of next week. The presentation will be at 2 o'clock in the room next door, and you're welcome to attend if you're available and interested. Her teaching presentation is going to be on the same topic as the teaching presentation from Dr. Fatah, so coagulation, flocculation. So if you don't want a repeat of that, I'd understand if you don't attend, but if you'd like to, I'd be glad to see you there. And I'm going to be posting another 10-point homework bonus if you're available to attend for submitting your feedback and a summary of the presentation. So does anybody have any questions about the announcements? Okay, so today's material is also covered on pages 37 through 57 in the textbook, and hopefully your textbook has arrived if you ordered that in the mail. If you want to get an A or a B this semester, I think you should read pretty consistently the material that's covering sections from class. If you're happy with a C or a D, then probably you don't need to read the book. But it just all depends on what you're hoping to learn this semester and what grade you'd like to achieve. So please read through the book. I think it's really important stuff. And what we're talking about today is a little bit abstract with reactors. Just to refresh your memory, what we've been talking about with reactions, mass balance, and kinetics is the idea that whether it's a physical reaction or a chemical reaction or a biological reaction, all three of those are processes that we in environmental engineering have to be aware of, because sometimes we're trying to physically separate things with some sort of a reaction. Sometimes we're using bacteria or other biological systems to break down a pollutant. Sometimes there are chemical reactions, but for all three, we're going to be keeping track of the flow of things in and out of a system that we're interested in, whether it's a reactor or a tank, or if we're keeping track of the pollutants that are coming out of a city. The system could be the city itself. But the rates of the reaction depends on the kinetics of the reaction. And today we're going to be thinking more about the volume that reactions occur in. So here this V with the cross through it, remember, means the volume that the mass is accumulating inside of, and that sometimes there's either a production or a consumption reaction that's happening in a reactor. So here's a sketch of a continuously stirred tank reactor, which is one type of reactor that we're going to learn about this semester, where there's constant flow in and out of a certain volume, and the reaction happens inside of the tank. So an example of a real-world continuously stirred tank reactor would be in a wastewater treatment plant, where in an aeration basin what we're trying to do is encourage bacteria to break down biochemical oxygen demand. So the other broad class of reactors that we're going to learn about this semester are plug flow reactors, and this is a sketch of a plug flow reactor that's using a screw at the bottom to carry the sludge off the bottom of a plug flow reactor. But we're going to talk about how these different reactor types influence kinetics and the rate of how quickly things are produced or broken down. So the simplest situation is when a reaction just happens without any inflow without any outflow, and without any movement during the reaction. So if we just pour some sort of a mixture into a tank and we mix it during a certain period of time, but while mixing occurs, there's no flow in and there's no flow out. And a mixed batch reactor is a situation like this, where the reaction occurs with no transport during the reaction. And when the reaction is finished, then we would drain the tank. So if some of you have seen a wastewater treatment plant before, one of the newer types of wastewater treatment plants is called a sequencing batch reactor, where what they'll do is they'll have wastewater coming in, let's say for an 8-hour period, they'll fill a tank. Then for the next 8 hours, they'll have a reaction, like aerating it. And then for the 8 hours after that, they'll drain it. And so what they need to have is they need to have 3 parallel trains, so that at any given time, one of the tanks is filling, one of the tanks is reacting, and another one is draining. That would be an example of how you could use a mixed batch reactor in the real world. So that section of the book that I encourage you to read through has these tables of reaction behavior in different types of reactors. So this is showing you, if you've got 0, first, or second order kinetics, which formula you should use in order to calculate what's called the mean retention time for a different type of batch reactor. So take, for example, if you were trying to figure out how long it would take for a chemical to go from its initial concentration C0 down to a lower concentration C sub T, when you know the rate constant K, then you'd use this formula to tell you how much time it takes for that reaction to occur. So for first order kinetics, you can see that we're using the logarithm function. In second order kinetics, remember that when we were trying to identify the second order kinetics, what we were graphing was 1 divided by the concentration, and that substituted into the batch reactor performance gives us this formula to calculate the time. So just in case you're not seeing it, T theta is equal to, for example, the first order ln of C divided by C0 divided by C sub T divided by the reaction constant K. So this is how much time it takes to go from the starting concentration down to some other concentration. This isn't necessarily the finishing concentration, it's just the concentration at time t. And then t is how much time, k is the rate constant. So this theta, you're going to see that several times this semester. Sometimes theta would be used instead of t. Some books just say theta. And what it means is the residence time inside of a reactor. How long it's, how much time the reactant spends inside of the reactor. So T0 is equal to this term for zero order kinetics, this term for first order kinetics, and this term for second order kinetics. We can rearrange this table though to solve for in terms of, if you know how long it's going to be in the reactor, what would be the finishing concentration? So now this table on the right is just telling you C sub T, the concentration at some time t, is equal to C0, initial concentration, minus K times T for zero order kinetics. For first order kinetics, you can see it's C0 times e to the minus KT. So we've seen this before. I think we did some examples in class on Wednesday with these formulas. And so the simplest case is that the reaction is happening inside of a tank with no inflow or outflow. Any questions so far about a mixed batch reactor? Why do we have to mix it? If it wasn't mixed, then let's say we had a tank and it's got water and some other stuff. Maybe the other stuff settles to the bottom. And if the other stuff settled to the bottom and the water's above it, then the concentration down here at the bottom would be different than if the concentration was completely dispersed everywhere. So we don't necessarily know if there would be some like localized hot spots of elevated concentration if it wasn't completely mixed. So this is only true if it's completely mixed, that we'll get this ideal batch behavior describing the conditions. All right, this is a very nice picture to a place that I've never been. I'd love to go sometime. I actually don't know where that is. I assume it's somewhere in the South Pacific, but I wanted to show you this picture because this is a really nice lagoon. A lagoon is like an inland water area. You know, like this is the ocean, and then the lagoon is shallow. Not a lot of wind-driven waves, not a lot of swell. This is a different kind of lagoon, a sewage lagoon. So it's an example of a mixed batch reactor. You know, you'd have the wastewater come into a tank, and it could sit there, in the case of a sewage lagoon, sometimes for a month before you finally take the water out. I'd rather go to this lagoon. Okay, the next type of reactor we're talking about today is a plug flow reactor. So a plug flow reactor, we can think of that as a pipe where the reactants enter one end of the pipe and they flow through the pipe and then come out at the end. And in a plug flow reactor, for it to be ideal, what we assume is that there's no mixing. Once the stuff gets into the pipe, it's not getting mixed up. So plug flow assumes that, for example, if you had water flowing through here and then for just a brief moment you replace that water with vegetable oil, then what would happen is the oil would flow through as like a distinct plug and it wouldn't spread out. Or what if, to make the example even more like corresponding to how things are really, what if we had like a dye, food coloring, and it's water soluble? So it's not staying as a plug simply because it's not able to be dissolved in water. But what if we had water flowing through, but we injected a plug of food coloring? In reality, the food coloring is going to spread out because of dispersion. It's going to spread out because of mixing inside of the pipe. You know, we know from reality, from fluid mechanics, that when water flows through a pipe, the pipe resists flow. And so if the water is going towards the right, the pipe is pushing on the water, and then what that does is it introduces a velocity profile, where in the real world, the velocity at the center of the pipe is faster. When you're further away from the edges of the pipe, there's more flow. We're ignoring all of that. In a plug flow reactor, we assume that everything flows without mixing. We're ignoring the effect of a velocity profile. We just assume that if we inject it at the inlet of the plug flow reactor, it's completely mixed across the cross section, and then it exits the plug flow reactor all at the same time. We have ways of accounting for reality, but we have to understand kind of like the ideal case before we get any further. So again, we have this idea of mean retention time, T sub theta, sometimes just called theta. That means how long the reactant spends inside of this reactor. And so the residence time in the reactor, as it's sometimes called. It's just time is the velocity divided by the flow rate. So time, for example, how many seconds it spends in the reactor is going, V is volume, not velocity. So volume, so think about, for example, cubic meters divided by the flow rate Q flow rate in terms of cubic meters per second. So if we look at the units of volume divided by flow rate, then what's left over is the seconds, which was in the denominator of flow rate. So that's how we get units of time. So how big is the pipe, the volume that of fluid that could occupy that pipe divided by the flow rate will give us the residence time. Let me clarify that so it's more obvious in future semesters. It's volume divided by flow rate. Sometimes to emphasize that we mean volume, V with like a cross through it, sometimes that means volume. So you may also see that sometime this semester in the notes. V with like a little cross through it to differentiate between volume and velocity. So here we've got some equations for plug flow behavior. Let's just skip back to the other one and compare plug flow with the batch reactor. They look the same, and they are the same. So ideal plug flow and ideal batch is the same, because if you think about it, what's happening is as the reactant is flowing through the pipe, we assume it's like a little tank that isn't being disturbed with any influence by what's on the left side of it, what's on the right side of it. So here you can see this shaded area. Just think of it as a separate tank that's flowing through the pipe, and it's not mixing with the surrounding fluid. And so even when we've got first and second order kinetics where the concentration influences the reaction rate, the concentration of reactant inside of this little plug is decreasing as the plug flows through the reactor, but it's not mixing up with the adjacent solution, so it has the same overall kinetics as a batch reactor. So you could think of it as like a series of buckets that's going through the tank. Like they're isolated volumes within a larger volume as the water's flowing through a plug flow reactor. So the equations for the mean residence time, you can see, are the same as they were for a mixed batch reactor. And if we are solving it in terms of the concentration, it's the same. So the reason why it's the same is because the fluid isn't mixing inside of the pipe. A plug flow reactor does not mix, is what we assume. And in reality, in the real world, we try to have plug flow reactors. So here's a series of pipes which will act as a plug flow reactor. I don't remember specifically what this was. It could be that it was UV disinfection, where inside of these pipes is like a lamp that's shining UV radiation to disinfect the water that's flowing through. It could be that, but I don't remember specifically. But any water that's flowing through this, the water that enters is isolated from the water that exits. It's at different concentrations, because as the water is flowing through this sequence of pipes, the reaction is occurring. The concentration, let's say if it's a consumption reaction, the concentration that comes in is high, and it's gradually decreasing, So first order kinetics, reactions are faster when the concentration is high. So what it means is that when the concentration is high at the beginning, the reaction rate is high. But then by the end, when the concentration is low, the reaction rate is lower. So this is a really important thing about plug flow reactors, is that the rate of the reaction is different inside the reactor. At the beginning, the reaction rate for a consumption reaction is higher and the reaction rate is lower because the concentration of constituents is higher going in than coming out. So that's a consequence of the fact that things don't mix inside of a plug flow reactor. Here's from a wastewater treatment plant an example of a plug flow reactor. It's a chlorine contact chamber. And the reason why they use plug flow reactors is they want the water to be in contact with chlorine for a certain amount of time in order to kill the bacteria that are in it before they dechlorinate the water. So this is a wastewater treatment plant. This isn't a drinking water treatment plant. If it was a drinking water treatment plant, it wouldn't be open to the atmosphere. They wouldn't want, for example, birds to be flying over it when they've got the finished water that they're about to send out to people to drink. But for wastewater, it's okay if it's open to the atmosphere, but you still do have chlorine contact to kill bacteria before you put the wastewater into the river. But the water is going to be flowing through these raceways, as they're called. So the water is taking this long, circuitous path to finally get to the outlet, and finally it goes out. If you didn't have these baffles in there, then the water would just go straight through, and it would mix. So the purpose of these baffles is to force the water to flow in a circuitous, unmixed way so that it doesn't short circuit the plug flow behavior we want to see. We want to have control over how long there's contact between the water and the chlorine, because it takes a certain amount of time to kill the bacteria. When you're looking at disinfection kinetics, the concentration times time is the dose. So it's not just what concentration of chemical you're exposing the bacteria to. It's the concentration and the time together that dictates the dose. So the design of the reactor, and you can see how it's got these shaped raceways. See the curvature? Why do you suppose that they bother curving that rather than just having square edges?
So you don't get pockets of water or concentration that just get trapped and stick.
Okay, yeah, because you wouldn't want there to be pockets of stagnant water. If we had, like, here's the raceway. If the water's going like this would be a pocket of stagnant water. And actually, it would be stagnant, but also it would be kind of swirling there. And it could introduce a little bit of turbulence. So it could disturb the unmixed character of the flow. So by having this guide around the edge, kind of like smoothly transitioning the flow around the corner, that's just a way of promoting what we want to see in a plug flow reactor. Like, it's intentional. In a plug flow reactor, we want there to not be mixing. The reaction happens faster in a plug flow reactor when there's not mixing than when there is. If there's mixing, then you're bringing the concentration lower and the rate of the reaction is slower. So plug flow reactors are efficient because the concentration is higher for the first part of the reaction. But they're difficult to build. Not everything is suitable for a plug flow reactor. Completely mixed flow reactors are very common. CMFR. Sometimes they're also called continuously stirred tank reactors. Civil engineering is adjacent to chemical engineering, and environmental is where they kind of meet on a few topics. And continuously stirred tank reactor is the terminology that's often used in chemical engineering. Completely mixed flow reactor is more commonly used in environmental engineering, but I'll sometimes use them interchangeably because they mean the same thing. What it means is that some flow comes into a reacting chamber, a tank, so to speak, and it's mixed. And so what that means is that the concentration inside the reactor, everything is the same. And then what comes out, the concentration of the effluent, which is the outflow pipe, the concentration of whatever we're interested in the effluent is the same as the concentration in the tank. Like there's no way or any reason why the concentration of the outflow would be different from the concentration inside the tank if it's completely mixed. Now, of course, the concentration of the inflow It could be higher because it hasn't been diluted and mixed yet. So C naught is the inflowing concentration, or the starting concentration. C sub T is the outflowing concentration, where T means time. So how does it dictate how much time it spends in the reactor? Think about what controls the residence time inside of the reactor. Any thoughts about that? Well, how big it is. If it's a very, very large reactor, then the water will spend more time in there. If it's a small reactor, the water won't spend as much time. And then it also depends on the flow rate. If it's a slow flow rate Q, then that would tend towards a longer residence time inside of the reactor. A high flow rate tends towards a lower residence time. So it's really important to remember that in a completely mixed flow reactor, the concentration in the tank is the same. And that slows down the reaction compared to a plug flow. Because remember, most of the reactions we're going to be talking about this semester are first order kinetics. Zero order is uncommon. Second order is uncommon. Most of what we do is first order kinetics. And in first order kinetics, the rate of the reaction is influenced by the concentration in the reactor. So think about, this is the place where the reaction is happening, and as soon as the chemical or whatever comes in, it's immediately diluted. And so the rate of the reaction is going to be slower than it would have been in a batch reactor or in a plug flow reactor. So we do now have different equations. These are not the same equations as we saw for plug flow and for batch reactor. This is different equations for the required residence time for a completely mixed flow reactor when we know some target outflow concentration we're hoping to get and the known inflow concentration. And here is the equations written in terms of if you know the residence time theta and you're trying to find out what will be the concentration as the water is flowing out of the completely mixed flow reactor. Here's a real world example of a continuously stirred tank reactor. And we don't have to stir it with an impeller. You can stir a tank by having air at the bottom and diffusing the air. The air will rise through the liquid and that'll cause churning and stirring. So we don't have to necessarily stir it with some sort of an impeller or a guy with an oar. It could be stirred just by injecting air at the bottom. So this is a physical example of an aeration basin. Okay, I've got some examples for us to work together. Let me pull it up on the screen and then hand it out. And I think I'm going to need to bring those equations up on the screen again as well. So let me hand out the in-class exercise to you. Okay, so this first problem, we're talking about organic compounds being removed by carbon absorption, 50 grams of methyl ethyl ketone dissolved in 33.3 liters of water. And we've got some kinetics here, the K value 0.08 inverse hours, first order kinetics. It's a batch reactor, and we want the final concentration to be 0.01. Okay, so let me paste over the equations for batch reactor. Let me go back to batch reactor. Here it is. Okay, so this is residence time, and this is for concentration in our batch reactor. Ooh. Well, that's a little awkward. So this is a multi-step problem. I didn't tell you what was the initial concentration. You had to calculate that from mass and volume. So we have 15 milligrams per liter as the starting concentration, and we want it to break down to less than 0.01 milligram per liter. And you know, that target could be related to some federal standard of what's allowable. It could be related to that's just our detection limit for sensing the chemical in water. It could be a variety of things, but that's just given as what we want the finishing concentration to be after it's been sorbed by the carbon. And then we know the kinetics of the reaction. So we're just simply substituting this into, this is a mixed batch reactor. And so this is going to be experiencing that idealized first order kinetics of breakdown. And it turns out that it's going to be 91.4 hours. And how would we know the kinetics? Maybe we did this experiment in the lab and then we're taking that K value out into the real world. And so you sometimes have to keep in mind that if you had a kinetic coefficient like this, it could be sensitive to things like temperature. So if you did this experiment at in an indoor lab where the conditions are warm, but then you're going to be doing the reaction out in the real world and maybe the water is cold because it's wintertime, it could be that the reaction doesn't perform as you expected because of temperature differences. So we always have to just kind of take our calculations with a grain of salt. These are just predicting what might happen based on the first order model, but there's a lot of real world factors that could adjust that. Anybody have questions about this first set of calculations here for the mixed batch reactor? Okay, question 2 is plug flow behavior. So water goes through this narrow, very long trough here. So the dimensions that are given, it looks like it's 5 meters wide. The depth of the water is 1.1 meter, and then 1,500 meters is the length. And then it goes into another back and forth raceway plug flow reactor that has 250 meters of length. 80 meters is the, I guess maybe, what we're talking about here is the overall volume of this tank, but it's broken up into individual raceways. And so it would be 250 is the length of it, 80 is the width, and then the depth of the water is 2 meters. So this is a first order reaction where we have the decay constant, K value. And it's a plug flow reactor. And what we want to know is what is the maximum flow rate that can be treated. So the inlet concentration here is 30 milligrams per liter. That C naught is 30. And the effluent concentration that we're going for is 2 milligrams per liter. And we know the volume of the reactor. We can calculate the volume, right? Because we got the volume of this inlet raceway. We got the volume of the secondary portion of it. Add them together. Okay, so let me paste in the formula that we know for first order kinetics, where what we're trying to find out is we know the inlet and the outlet concentration in this plug flow reactor. But we want to know what flow rate can we deal with. And so that's going to be related to the time, honestly. So let me just paste this same thing in again here. Solve for T, and then calculate the volume. If you know time and you know volume, that gives you flow rate. Q flow rate is cubic meters per second. So calculate the volume of the reactors and time
spent in reactors.
Okay, I've got the solution up on the screen. First, we need to find out how long the water has to spend inside of the reactor. So with the kinetics that we saw of 0.5 inverse days for the K value, to go from 30 down to 2, it needs to spend 5.4 days in the reactor. And now, that's the time that the reaction rate dictates it has to spend in there. And if we know the volume of the reactor here, if we add up the two parts of the reactor, it's 48,250 cubic meters is the volume. And it needs to spend a minimum of 5.416 days to reach the target effluent concentration. Then the flow rate that corresponds to that is 0.103 cubic meters per second. If the flow rate coming into the reactor is more than that, then it won't spend long enough time. If the flow rate is less than that, it would spend more time, and so then it would remove even more than the minimum of 2 milligrams per liter that we want to see as the effluent concentration. So plug flow reactor, where we're trying to find out the applicable flow rate. The last one, we'll have to hurry through this because we've just got 2 minutes left. Continuously stirred tank reactor. Inflow is 185 milligrams per liter. We know the flow rate of the reactor is 150 liters per second. And we've got first order kinetics with a K value of 6.15 inverse days. And we want 90% removal. So what 90% removal means is that we only want to have 10% coming out. So if it was 185 coming in, 18.5 going out is the effluent concentration. So let me show you the solution for this. 185 coming in, 18.5 going out. That's 10% of the initial amount remains at the outflow. So to calculate how long it's going to take in the reactor, we're now using a different formula than we did for the plug flow reactor, because remember, this is a continuously stirred tank reactor. So we use the different formula that when we substitute in the K value of 6.15 days, 6.15 inverse days, then it's going to need to spend 1.463 days inside of the tank. And if we have a flow rate of 150 liters per second, that's 0.15 cubic meters per second, which then you multiply the number of seconds per days. Then the volume of the reactor should be 18,960 is the required size of the reactor here. So let me give you a moment to copy that down. I apologize we had to rush through it. But it's just the same basic approach. We're just substituting in a slightly different formula because this is a continuously stirred tank reactor. Any questions? Okay, so let's just circle back to the announcements real quick. Remember that your homework assignment is due tonight by 11:59. Monday we're going to have a quiz at the beginning of class. Then your reactor homework assignment is due Wednesday at 1. Have a good weekend.